during the next 5 minutes is just to try to convince you that digital twin is not anymore a dream, but we can achieve it maybe in the next 2 to 3 years. But this is quite a nice challenge. And let's overview the key feature of the ideal power system grid digital twin. First, in my opinion, it has to be fast. If we want to help the operator, we need to give the condition of the network every 5 to 10 minutes. So this is quite a big challenge, and it has to adapt itself. Also, it has to verify that the parameters are good. It has to be synchronized with the power system. So we have discussed that before. On the other side, also, it has to be accurate enough. And like we mentioned, in some cases, we will need to use full EMT unbalanced simulation. In some other case, we can use Phasor, but with the addition of DER, then we will be forced to use EMT simulation. And in some case, and most cases, like we just discussed also, we need to use production code of the control. It will be much easier to use production code, real code, than trying to simplify that code and making a model out of it. So this is one of the main key features that all that together was preventing us to implementing accurate digital twin. And as of now, one of the big challenges that we were having, and since we were working on that since the last 15 years, is how to meet the speed challenge when we have to use EMT simulation. As of now, with conventional system, control room and planning tools, we're mostly using Phasor type simulation tool because it was much faster to use, take less computing resource. But now, if we want to go to full EMT simulation, now the number of cycles, when we need to simulate between 10 to 100 microsecond time step, then it means that the number of time step to simulate the same simulation run will be 1,000 times to 3,000 times more. So now, if it takes 2 or 3 hours to simulate a condition, then this is not practical to make a lot of tests and to help the operator. So because as of now, if you use a conventional EMT simulation tool, it will take you several hours to do maybe a 10 to 20-second run. So the problem is that how can we accelerate this type of simulation? And as of now, over the last 10 years, we have succeeded to implement quite large cluster that the idea is to use standard computer, really off-the-shelf computer running under Windows or Linux, and to implement it now on available supercomputer, or could be cloud-based, or could be in-house server. And the main structure that we are using now is to try to have a main grid simulator. And in this case, we need to have very fast, a lot of processor integrated with share memory to be quite efficient. And then we do like a real power system where we interface the plant model, like the DER plant models can be simulated on individual PCs or processor, and they are all connected to the grid. Same thing we have to do with protection control and also communication system, because communication will play a bigger and bigger role. So this idea here is to replicate, in fact, the structure of a real power system. So, and the good news is that when we go to EMT simulation, it's like in real life. We have the speed of lights that create delays in transmission lines. So we are able to simulate each part of the network subsystem in individual processors. So each station, each plant can be connected, can be simulated in single processor core, and they are all interconnected together by transmission line. So this physical characteristic enable us to scale the capability of the simulator according to what we want to simulate. So if the grid become very large, then we can just add a processor. So as of now, what we have demonstrated, at least over the last 6 months, is that now fast co-simulation that is required now to interface, for example, the 22-bit PSCAD DLL control model provided by suppliers. We need to interface that with either Linux or Windows simulator with 64-bit. So this has to be interfaced together, and sometimes we need to interface Windows DLL with Linux. So we need to have fast co-simulation that will enable to interface several type of simulation technology. Then also we need to support multi-rate simulation. It means we have to do with interpolation and extrapolation, because the rate used by the controller designed by the OEM may not. In fact, they are never the same rate as the rate of the main simulation, and different controller can be linked to the same system, so they all have the actual rate. So we need to be able to interface all this control and protection with their own rate, just like we have in the real power system. Now, how to interface these control models with the grid model, and now we try to follow the recommendation of the CIGRE IEEE committee that are trying to define an interface definition to use real code. So this is still a work in progress, but we are demonstrating that this is possible. Now we need to reach scalability also. I mean, we need to increase the size of the simulator to meet the needs. We cannot design the power system to meet the simulator. We need to design the simulator to meet the power system. And now one of the main challenge will also be the data management, model management, how to interface. And as you know now, there is no good standard to have the same database for EMT simulation. In the case of Phasor, there are some standard being developed, with the common interface model, the same model, but these are very not sufficient to implement full EMT simulation in the three-phase domain. So what we decide to develop over the last 4 years now is a kind of a common database where we can have the system data in both EMT mode and Phasor mode, and have a kind of a translation software in between. But then we need to take the data, and most of the time we need to take the data coming from models written with PSCAD or sometimes PSSC and or MTP. So we need to take this data because we don't have access to a corporate database, because in most companies, the PSCAD models or MTP model are made by engineers that maybe will pass the last 20 years of working just to maintain this data and make their own studies. So then we decide to make a central database here to be able to generate the model for IPSM, to be able to make parallel simulation of large power grid in EMT mode. We can even go and generate the FPGA code if we require. But also, we can take these same models and make parallel simulation in unbalanced grid with Phasor mode, because in most cases, maybe we'll need to have a mix of EMT with Phasor mode. So the idea is to reach the maximum accuracy, but to control the system data. I think at the end of the day, this will become, I think, kind of a standard technology in the next few years. But the model management itself is still a very big challenge. So our roadmap is to, of course, include many of the other popular software like DigSilent for distribution. We have the SIME, and now we are even thinking of maybe using the GridLabD from PNNL. And then I put here our competitor. Maybe we can interface the RSCAD from RTDS to have the data in the unified database here. And maybe this can be mixed with the unified modeling interface proposed by Vestas. But I think this will be quite a big challenge. So this is an example of the scalability here. This is the China network, the eastern side of China, where they have more than they have 10 to 20 HVDC link, and their main problem is here that if they want to simulate to evaluate the stability of their power system, you have many inverters connected to the same cities. Then there is a risk of communication failures that can stop completely the power transfer, and this cannot be easily simulated with it cannot be in fact simulated with Phasor type tool. So they need to use their what we call this is an hybrid analog digital simulator. In this case, they don't use the control code. They use in fact the real controller hardware. They go that far. So they have duplicate of the control system in their big lab, and then they simulate the complete grid to help the operator to take good decision. Now, when we go to full to system, like here, this is an HVDC grid. This was made by the CGRI before committee. Here, this is only made with full inverter. It's a multi-modular inverter system. Each of these inverters has thousands of switches. But then, even if it's complex, now we can achieve faster than real-time simulation at 25 to 50 microseconds with only 7 processors. So this is an example showing that we can scale up the models as we need. So one important point also is to be able to analyze cyber-physical system. And because now the communication system will play a major roles in the global system security and stability. So this is quite important to be able to connect the real, the real intelligent controller with the real code that will run in the control center, and interfacing that with a good emulation of the communication system, so that you can see the effect of delays in the communication system, of fault or errors. So this will become a part of the global system. So this is quite a challenge. So in summary, like we discussed with all the presentation, we may need in many cases to go to full simulations with using EMT models, and it can be combined with Phasor type model also. And right now, we demonstrate that in-house or cloud-based HPC can now provide affordable solutions to implement digital twin using EMT simulation. And because the price of this of adding more and more processors will go down over time. So the problem will not be anymore the computer, but it will be how to have good simulation efficiencies. And how are we able to introduce real production code and synchronize all the data and all the models with what we have in the field. So we believe that now we'll be able to get results for the system operator within 5 to 10 minutes, but not only for system operator, but for planning studies also, because the challenge will not be anymore the design, in my opinion. It will be how can you test your design, and there will be a limit in some case. Maybe we will need to reduce the complexity of the total system design so that we are able to test it. So design for test would be one of the main challenge. And then how can you test it? How can you test that your specification is good? And then now we have demonstrated also that model-to-model interface and simulation tool and interface is now possible using a database. But there are still a lot of development that we have to do over the next years, that how to automatically adapt the digital twin to initial conditions and connect it to the state estimator, how to get the real version of the controller, so how to test the validity of the model parameter, because many modifications can happen in the field without knowing it. So we need to find a way to validate that the models correspond to the realities, how to implement the good testing tools with maybe artificial intelligence based tool to help to analyze the total system and how to make better management of data models. So this is quite important. So I'm inviting specialists, new PhD people, specialists, if they want to collaborate to this existing project. We are very open to such collaborations. So thank you very much.